Good morning, class. My name is Dr. Arepo, and here's Pre-Calculus Practice Test 2, Module 2, covering Chapters 3 and 4. Review, here's Chapter 4, Exponential and Logarithmic Functions. We want to find the formula for an exponential function that passes through the given points, 0, 2000, 220. And of course, f of x is in the form of a b to the power of x. So basically, we are going to plug in. This is the pair, that means x is 0, y is 2000. This is the second pair, that means x is 2, y is 20. And remember, f of x is another way of saying y, of course. Everybody knows that. This is the same as y. So with that being the case, when we use 0, we get a, b to the power of 0 is 2000, and b to the power of 0 is 1. Resulting in a being 2000. So we can replace the a, it results in a being 2000. So replacing the a with 2000, we get 2000 b to the power of x being f of x. Now f of 2 is 20, so let's replace it. 2000 b to the power of x, x is being replaced by the x coordinate 2 is equal to 20, and now the second equation will give us the b. In other words, we really have two equations, two unknowns, two non-linear equations. Divide by 2000 and b squared becomes 1 over 100. b is plus minus 1 over 10. The base must be positive, so we accept only the positive 1 over 10. But bear in mind, this gives you two answers, plus minus 1 over 10. We accept the positive one, and we write y or f of x equals 2000, 1 over 10 to the power of x as the final answer. We deposit $10,250 in an account that gives us 4% compounded interest. How much will the account have after 10 years if the following situation holds, if it's compounded monthly? So why don't we plug in what we have? Here's the given, everybody. The amount of principal is given to be 10,250. The rate is 4% or 0.04. So we can plug it into the formula, replacing the P with 10,250 and R with 0.04. And we don't know N for part A. When it says monthly, N becomes 12. By the way, it says 10 years, you can replace the T with 10 also. I hope everybody's following that. So in the case of a monthly, we replace the N with 12. So look at this formula. All we have to do for monthly, N is 12. When it gets compounded annually, N is 1. Semi-annually, N is 2. Monthly is 12. So on and so forth. So obviously you plug it into a calculator and it results in $15,281.03. As far as the money is concerned, normally we go with two decimals when we do the rounding. How about if we do the same thing, but this time weekly? So if you go back to this formula again, all you have to do, change the N so it corresponds to weekly. So you have to change it to 52 and plug in to a calculator will result in a little bit more money. If you compare it to the monthly, this is a few bucks more, $15,288.85. Now, continuously, ultimately, this becomes E. So PE to the power of RT, it's the same P, $10,250, is the same R, 0.04, and it's the same T, 10. Plug into a calculator, and again, this is even more by a few bucks. If you do it continuously, you end up with $15,291.20. What is the doubling time? In other words, how long does it take for the original investment, which is this much, to double? And it's important to understand that in order to calculate the doubling time, you really don't even need to know what is the initial value. So how does that work? P is the principal that you begin with, then doubling means this will be 2 times that. So let's do that, 2P. And so we can cross out the common factor of a P. In other words, divide by P. And therefore 2 is e to the power of RT. We are going to solve this equation by taking a log of both sides. Since the right side has the base e, we take a natural log of both sides. So natural log of the left side is ln2. Natural log of the right side results in r times t. So it's important to see that t is ln over r and r is ln2, I'm sorry, ln2 over r and r is ln2 over t. So from here we have 2 equations. It's important to know you can calculate the r, you can calculate the t, whichever is missing. And we are interested in time. So t is missing, ln2 divided by r, which was given as 0.04. Remember, ln2 is a number. Then you plug in and you use a bunch of decimals, however many decimals that they ask you, you come up with the answer a little bit more than 17 years. So 17.329 years. We are given a bunch of graphs. We want to answer the following questions and all have the exponential form of ab to the power of x. By the way, I hope everybody remembers that the base must be positive and it can't be 1. So I'm going to remind you that what we learned is that b must be positive and it can't be 1. The right side over here, the base is larger than 1. The left side, if you will, b is between 0 and 1. This is reminding you of what we learned in algebra. So the question is, which graph has the largest value of b and which one has the smallest value of b? Graph D has the largest base value. Here's the reason. Remember, on the left side, those functions, b is between 0 and 1. On the right side, b is larger than 1. And the one that is closest to the y-axis, it rises faster, has a larger base, and therefore the answer is D. On the other hand, on the left side of the y-axis, they have values between 0 and 1, and then closest to y has the smallest value, and that makes it graph C. I hope you see on the left side, graph C is closest to the y-axis. So look at the y-axis. The one on the right, the closest is D. The one on the left, the closest is C. Therefore, the answers are D and C accordingly. Now, which one has the largest value for A? Which one has the smallest value for A? If you choose x to be 0, the answer becomes 0, comma a, which is the y-intercept. So 0, a is the location of the y-intercept. Therefore, the largest a, meaning the largest y-intercept. Look at which one has the largest y-intercept. Clearly, the answer is C. On the other hand, the same thing again, this represents the y-intercept. The smallest one would be what? This one. This one has the smallest value, the f function, the graph f. We want to use transformation of this function, f of x or y equals 2 to the power of x, and come up with this 2, starting with the basic one, f of x equals 2 to the power of negative x. First and foremost, the graph of y equals a to the power of x or b to the power of x when the base is larger than 1, it looks like this. This is an exponential growth. In general, when the base is larger than 1, it looks like that. I mentioned that last time. And so if you want 2 to the power of negative x, so what happens? As you change x to negative x, it flips over with respect to the y-axis, and it will look like this. So it flips over. So flip it over, looking like this. And obviously, your horizontal asymptote is not changing. Your y-intercept located at 0, 1 is not changing. Your domain of all real numbers is not changing. The range of 0 to infinity is not changing. You can write all of those. So this is the function y or f of x equals 2 to the power minus x. Horizontal asymptote is the same. Domain, range, they remain the same. The difference is this is an exponential growth. This is an increasing function. This is an exponential decay. This is a decreasing function. Now, as far as part B is concerned, we are looking at the original function, the basic elementary function y equals 2 to the power of x, one of those functions that we should be familiar with. It moves up by 1, so we shift it up by 1 unit. So what happens when you take it up, you changing the location of your horizontal asymptote, and it has no effect on the domain, but it changes the range. So take a look at what happens here. We shift it by 1 unit, and therefore it creates a different horizontal asymptote. Therefore, when you go to this function, the horizontal asymptote changes from y equal to 0 to y equals 1. The domain doesn't. And therefore, the range, which was 0 to infinity, also changes, goes up from 1 to infinity. One interesting point would be to look at this one, which has coordinates 0, 1. And the new one is located at 0, 2. And this is our horizontal asymptote. We are given the function f of x equals 4 to the power of x. We want to write a function that results from the given information. So we have this one, and we want to move it 3 units up. So add 3. We want to move it 5 units left. So x changes to x plus 5. Reflected about the x-axis. So with respect to the x-axis, if assuming this one has a positive y, then the other one must have a negative y. So that's why you put the negative sign in front of a function. So this changes to negative for x, whereas reflection about the y-axis, here's the y-axis, okay, if it's right, goes to left. So if it's x, becomes minus x. Here's the given graph. We start from 2 to the power of x, and we write equations to get there. As always, it's an elementary function. We should know the graph. Now, notice the shape. This goes up like that. This goes down like that. So if you flip it over with respect to the x-axis, so we flip it over with respect to x-axis, that's what happens. So let's write this one has a y-intercept of 0, 1, whereas this one has a y-intercept of 0, negative 1. And so when you compare these two, you notice they are practically the same, but it has been shifted up. And so this 0, negative 1, this is the y-intercept, now has the coordinates. Let me write it. 0, 2. Therefore, from negative 1 to positive 2, we went up by 3. So it has been shifted up by 3 units. And so y equals 3. Is the horizontal asymptote. So a quick recap, you have the general shape of a 2 to the power of x, you flip it over, becomes minus 2 to the power of x, and you bring it up by how many points. You can see from negative 1, it has gone up to 2. I'm looking at the y-intercept, that's giving me number 3. So justify every step. We want to rewrite the equations, and as long as we remember the general formula, we should be fine. Remember, this is the base, this is the exponent. So you want to go this route. Let me do this drawing. If you go this route, that means 5 to the power of q is m. You want to go this route. Now, when you don't have a base, if it's ln, the base is e. So e to the power of z is v. And if you don't have a base and it's log, the base is 10. So that's what we have. This is a natural log. This is a common log, as everybody knows. The reverse process, if we are given the exponential format, how do we rewrite them in the same manner? As long as we understand the relationship between the two, such that if we go back to, for example, part A, both have base 5, both have q as the exponent. So now this one we are going to go with log. The base is 3 and the exponent is x goes to the other side. So log y base 3 equals x. Log y base 3 equals x. In this case, because the base is e instead of log, we use ln. So ln of h is k. In this case, log base b, the base is 100. Log base 100 of b, my apologies, is equal to a. The base is 100. So look at all cases. The base is 3, so it's here. The base is e, we mentioned ln. That takes care of it. The base is 100. It's right here. So Here's the synopsis of what you need to know in order to have an easy time with logarithmic and exponential functions. The relationship, first and foremost, is that first of all, b is larger than 0, b can't be 1, and y equals log x base b is equivalent to x equals b to the power of 1. Now, if you look at these two, the way we compare them, they both have the same base b and the same exponent y. As long as we can see the relationship between the two, we are in good shape. And generally speaking, if you have a log and exponential with the same base, they are inverse functions. As an example, y equals e to the power of x versus y equals ln x. Take a look. They are inverse functions, therefore they are symmetric with respect to the line y equals x. Also notice this is y equals e to the power of x. As I mentioned, when the base is larger than 1, that's the general shape. And the same thing for the log. Any log when the base is larger than 1, it looks like that. If it's between 0 and 1 is a different story. And so we have the general logs. For example, log 1 with any base is 0, log b base b is 1 when the base and the argument are the same, the answer is 1. Log b to the power of x when the base is b is x, b to the power of log x base b is x. These two refer to the fact that the two functions are inverse of each other in general. I'm talking about general logs, whether it's e to the power of x and ln x or general log with any other base. And this is called the product rule. Log of xy is log x plus log y with any base, for example, base b. Log of x over y is log x minus log y with the same base, whatever, for example, b. And log x to the power of n is n log x with the same base b. In other words, n becomes the coefficient. Now, this is the general case. If you truly have an easy time with that, you can go to the natural log and make it for base e, for example, ln1. The two that I want you to pay attention to is the following. I guess all of them are pretty easy. Take a look at the fact that these two, say the functions are inverse of each other. Take a look at this. Ln of e to the power of x is x. E to the power of ln x is x. You're going to come across this in your courses. You really should get very comfortable with this. And here's for the common log when the base is 10. Log of 10 to the power of x is x. 10 to the power of log x is x. Of course, there are other properties, but those properties especially, I've noticed sometimes students have a little bit of a difficulty with that. And of course, this is the change of base formula, which says if you want to calculate the log with any base, you can take it to any other base. Normally, we use either common log, so we say log x over log b, or natural log ln x over ln b to calculate it, and most calculators can't handle any other basis. All right. Let's see what type of a transformation takes place so we can state the domain, vertical asymptote, and the rest of this stuff. So we have log x. When we go to log x minus 7, that means we're going to shift it to the right by 7. So what happens is this is log x. And as we shifted 7 units to the right, notice this has location 1, 0. And now the new x-intercept at 8, 0. So this one has a location 1, 0. Now 1 plus 7, 8, 0. And so we want to answer this question. So let's redraw that and take a look at this vertical asymptote. In general, if you set the argument equal to 0, that gives you the vertical asymptote. So x minus 7 equal to 0, x equals 7 is your vertical asymptote. So don't forget, this is your x-intercept at 8, 0, vertical asymptote x equals 7. And the rest is pretty obvious. The domain starts from 7 and goes to infinity. 7 is not included. Range, we have no restriction, is all real numbers. the end behavior as x goes towards 7, f of x goes towards negative infinity, and as x goes to infinity, f of x goes to infinity. They both blow up. Now, what I want to mention here, really the better notation for that, it's coming up in your calculus courses. It's going to say as x approaches 7, and this would be 7 from the right, it's red. 7 from the right, 7 from the left. In this case, 7 from the left, the function is not even defined, 7 from the right. ln of 2 minus x, we want to do the same thing, and therefore we are going to start with ln x and go to ln of minus x, which simply put, it will flip over with respect to the y-axis. Remember, you're changing x, if assuming x is positive, now negative is on this side, so you flip that over. Therefore, if you have this x-intercept at 1, 0, the new one would be negative 1, 0. Let me write that for you. So this is located at 1, 0. This is located at negative 1, 0. Now, we are looking at this. We put that in a parentheses, and then we put a negative 2. I hope you realize this makes it minus the parentheses x minus 2 minus x plus 2, or 2 minus x. This is the methodology to see, therefore, that it has shifted, but it has shifted what? To the right now. So this was the original one. This is the new one. This is ln of minus x. And now this has shifted to the right by 2 units. So this is ln x. This is ln minus x. And this is the one that has been shifted. To make sure we understand, let me just graph this way so you can easily see what's going on. And when you add 2 to negative 1, it gives you 1. I hope you see why it goes back to the original x-intercept. And so as you can see, we have the vertical asymptote. If you set this one equal to 0, 2 minus x equal to 0 gives you x equals 2. So that's the vertical asymptote. So the result is that the domain is from negative infinity all the way, and it stops at 2. The range, we have no restrictions. So domain and range, domain from negative infinity to 2, range all real numbers. And notice, as far as the end behavior, as x goes to 2, g goes to negative infinity. As x goes to negative infinity, f of x go to infinity. First of all, let me just change this to G class. Then I want to add a couple of things. Now, notice as we get closer and closer to 2, this goes to negative infinity. And when x goes this way towards negative infinity, it blows up to positive infinity. And again, the methodology that you see here, instead of that, you would see x is approaching 2 from the left in calculus. So it's important to know that this doesn't mean negative. It means 2 from the left. Numerically, 2 from the left, you can think of it as 1.9, 1.999, so on and so forth. Here's the next question. We want to look at transformation, starting with a basic function log x. This is negative log 3x minus 4 plus 3. So we are going to look at log x first and see what happens. We look at log 3x, and therefore, if you look at log x taking place the x-intercept at this point, which is 1, 0. Now, what is the effect of 3x? That shrinks along the x-axis by a factor of 3. Remember the effect of that. Therefore, look at what happens. Your new x-intercept is 1 divided by 3, because this was 3. If it were 5, would be 1 divided by 5. So this point now has coordinates 1/3, comma 0. And I wanted to emphasize this x coordinate, if you will. The next one is that we want to make it into 3x minus 4. So we do have the 3, we put a parenthesis here. What do we need here to make this a 4? We need minus 4/3. Please understand, if you distribute, you get 3x minus 4. Why is that important? Because we can't assume that it has shifted by 4 units, but rather by 4/3, and negative means to the right. Therefore, the original one is this one, then it shrinks by a factor of 3, then it moves by 4/3, and as a result, 4/3 with 1/3, they add up to 5/3. So the original x-intercept at 1, 0, now it's as 1/3, 0, and so far we've reached 5/3, comma 0. So we are here. I hope you realize this is the same as this one. We haven't accounted for the negative yet. We will do that by flipping it over. So as you're looking at this case, you flip it over with respect to the x-axis, because the negative is in front of the whole function. Okay, so this is the function we were looking at. Flip this over with respect to the x, and it looks like this. Looks like this. And so what happens to your x-intercept? It doesn't change, because it just flips over. The 5/3, 0 remain unchanged. And now we are going to move that up by how many? By 3 units. So we are going to move it up by 3 units. So this function moves up by 3 units. It looks like this, and it's hard to see what happened. That's why I like to separate it into a single one. And so what happens here is that that creates this vertical asymptote. It's important to see a vertical asymptote. Always you set the argument, in this case 3x minus 4, the argument of log equal to 0. That would be your vertical asymptote, VA x equals 4/3. And as far as your old intercept is concerned, remember this was 5/3, right? So it's the same thing, it's just gone up by how many? By 3. Therefore, 5/3, comma 0 goes to 5/3, comma 3. I want to make sure everybody understands what's happening here. When we shift this one up, we did not change the x coordinate. So 5/3 remains as 5/3. The x coordinate was the same, but the y coordinate in all cases was 0 until now that we've added 3. Therefore, we can write the domain. We got the vertical asymptote, starts from 4/3, goes to infinity. Range, we have no restriction, negative to positive infinity. And the end behavior, as x goes to 4/3, h of x goes to infinity. As you can see, it goes up, it blows up to infinity. And as x goes to infinity this way, then h goes to negative infinity. And by the way, this 4/3 also, we would write this as x approaches 4/3 from the right, as far as the notation in calculus is concerned. That's what you are going to see. We want to expand using the rules that we have seen. We should have no problem with that. This follows the product rule. So log of x plus log of y plus log of z. And don't forget to use the same base. This one uses the quotient rule, log of the top minus log of the bottom, and use the same base. In this case, it's ln natural log base e, so ln 9 minus ln x. We are looking at the power rule. The exponent sits in front and becomes a coefficient. We are looking at combination of power rule, product rule, and quotient rule. So we can write this as follows. Log with any base, the base is x. Don't forget just to repeat the base of a squared b to the power of 4 minus log base x of c to the power of 7. In other words, I'm using the quotient rule. I'm separating the top from the bottom. I'm using number 6. Now, this one, I can use a product rule and cut it into 2 pieces, log of a squared plus log of b squared. And finally, this one, this is b to the power of 4. This one, the 2 sits in front. This one, the 4 sits in front, minus, in this case, 7 becomes a coefficient. All of them having the same base. So we are expanding the logs. I'm going to continue with the same thoughts here. In order to expand this, we can rewrite this as x cubed, y to the power of 5 in a parenthesis to the power of 1/2. Now we can bring the 1/2 in front. And now we're going to separate into log of x cubed plus log of y to the power of 5. Now 3 sits in front here, 5 sits in front here, and 3 times 1/2 becomes 3/2, and this becomes 5/2. So I hope everybody can see what's happening here. So a quick recap. First, we change this to 1/2. Then we bring the 1/2 in front. Then we separate these two into log of x cubed plus log of y to the power of 5. Let's also write this step. So you can cross out the 3, put it in here. You can cross out the 5, put it in front, and now multiply by 1/2. Part B is very straightforward. There's not much to it. Log of the top minus log of the bottom. And don't forget the same base. In this case, natural log. So ln of x minus ln of the parentheses, and you write the bottom, and there's nothing you can do to separate them. It's done. This part is done. Here's the next one. Log base 4. And we see a bunch of terms at top. So we are going to use the quotient rule to separate the top. So log of the top from the bottom minus log of the bottom. So that is the first step we need to take. Now, there are a couple of steps involved. So we are going to separate them into log base 4 of square root of x plus log 10y cubed root. So I'm looking at these two pieces. We don't have to worry about the third piece. The third piece is very simple. 10 sits in front, and that's done. And we can rewrite this square root of x as x to the power of 1/2, and we can write this one as 10y to the power of 1/3. So I hope you see that you get 1/2 log x with the same base, whatever the base is. Plus 1/3 log of 10y, again, the same base. So this piece is done. This piece, we can separate this into log 10 plus log y. This can be separated into log 10, log y. Both of them have the same base, namely 4. And now let's finish the job. So this one, you write it. This one is 1/3 log 10 base 4. This one is 1/3 log y base 4. And this one, number 10, sits in front. And here's your final answer. So a quick recap. Notice square root of x becomes x to the power of 1/2, and it sits in front. Square root of 10, cube root of 10y is 1/3. That's how we get that, 1/3 of that. And we separate the 10 from y. So log 10, and this is log y, both of them are 1/3, and this one, 10, sits in front. You could do this even in one shot. It's really not that bad. It is absolutely up to you if you feel comfortable. But you have to show some work to your reader. Now we want to put them back together into a single log. Again, we are going to go back and forth with the properties that we have learned. So in this case, log of this times that. So it becomes log of 2x to the power of 4, 3x to the power of 5. And you have the answer. If you look at part B, we are using the quotient rule. So it becomes the ln of 6x to the power of 9 over x squared, which is ln of 6x to the power of 7. When we look at part C, I would get rid of number 2 and put it here. Here's my next step. I'm going to get rid of number 3 and I'm going to put it up here. And now I'm going to multiply the arguments x squared and x plus 1 cubed, and that's my log. So I'm using this one and I'm going this way. I'm going to multiply x squared by x plus 1 cubed. Now, again, you can do this in one shot. Please understand, anything that has a positive sign basically goes at top. Anything with a negative sign goes at the bottom. So you can do it in one shot. But just the way it is, let's make some changes first. Let's do get rid of the 1/2 and put it here. Let's get rid of the 3 and put it here. And not that you have to make these changes, but I'm going to do that so to make sure that you can follow. I can rewrite this as log x plus log z cubed minus log y to the power of 1/2. I'm going to put it as a square root. These two give us log x z cubed, and then we divide by square root of 1. Now, do you have to take all those steps? No, as long as you show a step or two, that's good enough. It depends how comfortable you feel about the process. So, logarithmic rules, putting them together or separating them, expanding them. We should be able to do both. We want to solve some equations. First, we're going to look at cases like this, where we are dealing with the same base. If we have the same base, the exponent must be the same. If we have the same exponents, the bases must be the same. So this one, simply put, they have the base 5, so the exponents must be equal. Set them equal. And I hope you realize we can take this to the other side and add it to minus x, and it becomes a 3x. Divide by 3, x is negative 1. It's always a good practice to check. That means go back to the original one, make sure it works. When we look at part B, they don't seem to have the same base, but as we look at them, we notice, well, maybe we can use the base 4 for all of them. How do we do that? We know 64 is 4 cubed and 16 is 4 squared, so let's write it. Based on the exponential rule, we can add up the exponents, so the left side becomes 4 to the power of 3 plus 3x. Let me just write that for you. So the left side is 4 to the power of 3 plus 3x, and the right side is unchanged. Therefore, 3 plus 3x is 2. I can subtract the 3 from both sides. 3x becomes negative 1. And division by 3 results in x being negative 1/3. If I want to solve part C, first I divide by 2. And now in order to get to the exponents, I need to take a log. Since the base is e, I'm going to take a natural log of both sides. So ln of the left side, which is 3x, equals ln of the right side. And please understand, ln of the right side is the number, ln 13/2, that you can use a calculator to get to. Now, division by 3 gives you the precise answer. Now, this is the exact answer. And then this is an approximation with a bunch of decimals. How many decimals? It depends. When you look at part D, you can do by substitution, let e to the power of x be anything except x, like y, and it becomes y squared minus y minus 6, or do it just the way it is. If you want to go that route, let y or z or m or u or any variable except x represent e to the power of x, in which case you're dealing with y squared minus y minus 6 equal to 0. You factor, replace the y with e to the power of x, come up with the answer. Or you may notice that, well, I can factor it just the way it is. This is e to the power of x minus 3 times e to the power of x plus 2. I hope you realize this is y minus 3. Let me write that in case. Times y plus 2. So you could have gone either way, with or without substitution. This results in e to the power of x equals 3. And this results in e to the power of x equals negative 2. I hope you know that e to the power of x can't be negative 2. As you recall, the range is from 0 to infinity. You remember the graph. So this has no solutions. This gives you x equals ln 3. And that is the precise answer. And with a bunch of decimals, it's a rough estimate. So this has no solutions. All right, we start with the first one, log 9k base 3, or you can say log base 3 of 9k equals 2. So by definition, look at the definition, you just rewrite it. 3 squared is 9k. And I hope you know that 3 squared is 9, therefore k becomes 1. As always, you can check your work. Anytime you want to solve a logarithmic equation where one side has a bunch of logs, one side has a number, or both sides have numbers and logs, bring all the logs together into a single log, bring all the numbers together. This is log of negative 20x. And now you go by definition. So negative 20x is 10 squared, whatever the base is. Remember, the base is missing with log. That means the base is 10. So you bring it into a single log and you have a number. You go to the definition of a log. Minus 20x is 10 squared, which is 100. And divided by negative 20 gives you negative 5. So x equals negative 5. It is important to know that logs cannot have a negative argument. So if you go back and check it, so this guy is a number and it's fine. This guy, negative times negative makes it positive, therefore is acceptable. All right, if you look at this case, two logs are identical. If they have the same base, they must have the same argument. Let's do that. So 5n minus 2 is 8 minus 5. And it's not that we drop that. They have the same base. They must have the same argument. And that's an easy case. You can bring the negative 5n here. You bring the negative 2 to the other side, becomes positive. And therefore, n becomes 1. You can check it and make sure none of the argument is negative. I highly recommend you always check your work. We notice both sides have logs. So on the left side, we have a single log and we're done. On the right side, let's put them together into a single log. So x times 12 gives us 12x. Now both sides have single logs. Therefore, the argument of the left, which is x plus 12, is equal to the argument of the right, which is 12x. We drop the x and this changes to 11x. We are, in other words, subtracting x from both sides, and we are dividing both sides by 11, and that's the final answer. Again, you want to check, make sure none of the arguments is negative when you plug in. This guy 12 over 11 is good, this one is good, so we are fine. If you look at the first one, both sides have logs, so let's bring each side to a single log. The right side is, put the left side into a single log by using the rules that we have learned. This becomes ln of x plus 4 over x, the quotient. Since they have the same base, they must have the same argument, so x plus 4 over x must be the same as x plus 1. And we do the cross product. This remains, this becomes x squared plus x. I hope everybody is comfortable with cross product. We can drop the x from both sides. X squared equals 4. X is plus minus 2. You go back to the original equation and you check, negative 2 will not cut it because it creates negative argument right here. You don't even have to check this one, although it does the same thing. Understand it's fine here because negative 2 plus 4 is positive 2, but over here it creates a problem, and that's out. One side involves logs. We bring that together by the product rule. So log of x times x minus 1 base 2. And the right side is a number. There's nothing else we can do to simplify this further. We go with the definition. We go this route. X times x minus 1 is 2 to the power of 1. Please understand whatever this is, the base to the power of that. This is x squared minus x. You move the 2. So one more time, x times x is x squared. X times minus 1 minus x. You move the 2. And this is an easy factor. So we factor into x minus 2x plus 1. X is either 2 or negative 1. We go back and we check 2 works. If you plug in negative 1, this one is giving us a negative argument and it's out. By the way, you can't even have a 0. I want you to know that. Even 0 is not acceptable because the domain is 0 to infinity for basic log. We want to solve these equations. The first one is to move the 10. 4 to the power of x is negative 7. It can't be, just like the question we dealt with regarding e to the power of x, and that creates no solutions. 7 to some power is 1. 7 to what power is 1? I hope you realize and you remember 7 to the power of 0. Therefore, the exponent must be 0, which creates x equals 10. And obviously, you can check your work. Now, this is the most difficult type when you can't do anything about the base or the exponents. None of them is the same. And then you have to either take a log or natural log of both sides. If any of the bases has base e, you go with natural log. If any of them has base 10, you go with common log. If not, then you choose, and it makes no difference what you choose. Let's take natural log of both sides. Then x sits in front, in this case, x minus 2. Please understand, ln 4 is a number, but we're going to keep it as ln 4 because it's an exact number. So is ln 9. So we can, you can think of it as a number. We can distribute, okay? Now you're solving for x. Everything involving x must come together. So all you have to do, move this one, make it minus x ln 9. Now on the left side, I can factor out the x. And if I divide by the parentheses, I have the exact answer. Of course, you can plug it into a calculator and approximate. The other thing I want to make sure everybody understands, if you did a different movement here, you could have ended up with the following, and I want you to see they are both the same. If you look, pay attention that this has a negative sign. So if you ended up with 2 ln 9, so I am making it positive, over ln 9 minus ln 4, I hope you see that the two are identical. I'm writing it just to make sure we know there is no difference between the two. Depends on how we move things around. If we assume log 2 is given as A, log 3 is given as B, and log 5 is given as C, with some base that we don't know what it is. We don't know the base. That means we can't calculate those values A, B, C, and we want to see how we arrive at the answer here. So here's the last question we are going to do. So we're going to cut 50 into its factor that, in fact, its factors that include 2, 3, 5, whatever we can. I hope you realize this is 2 times 25, which makes it 2 times 5 squared. I'm assuming nobody has any problem with the factor. Therefore, this is log 2 plus log 5 squared. And of course, makes it 2 log 5. And we keep the same base. As I mentioned it, even if I don't mention base B, because the original one had B, we keep it. And now log 2 base B is replaced. So is log 5 base B. So we have A plus 2C, and we are done. So it's all a matter of factoring. Same thing happens here. First of all, this is 300 to the power of 1/5, and 1/5 sits in front. That's the first thing. The other one is to factor this. An easy way to remember how this is factored is 0, that means 10, which is 2 times 5. So this is 2 times 5, this is 2 times 5. So that means 2 squared, 5 squared, and then we have it 3. I'm assuming everybody's okay with the factoring, and I'm just reminding you an easy way. Every 0 corresponds to 1, 2, and 1, 5, okay? So now this we will separate, becomes log of 2 squared plus log of 3 plus log of 5 squared. Log of 2 squared, 2 sits in front. By now, I'm assuming everybody's comfortable with that. So we have the 1/5. When you separate this, 2 sits in front. This one is log 3, 2 sits in front. This is what we have. So 1/5, and now log of 2, we replace it with A. So this is 2A. Log of 3, we replace it with the B, and log of 5, we replace it with C. We get 2C. Bear in mind, all of them have the same base. Best of luck, everybody.